Welcome to physics for January the 27th. As usual, before we get started into the new stuff, let's talk about generic announcements. Tutoring. The tutors have told me that they're not getting a lot of business. A lot of people aren't showing up. Hang on a sec, somebody just arrived. Let me let him into the class here. Okay. So the tutors tell me that a lot of you aren't coming by to get help. You need to be aware that Principal Wilson is paying the tutors to be there to help you, and he's not going to keep paying them if we don't start getting more people showing up. So really important that you guys show up. Tuesdays and Thursdays, right after school for an hour. Fridays in the middle of the day. And then Saturday, we have one in the middle of the day and one in the late afternoon. Look on Canvas to find out the exact times or send me an email. Please take advantage. Now, also, I've had one or two students tell me that they're a little concerned that it's hard to get a hold of me personally outside of class hours. The other teachers, they all have what they call office hours between 9 o'clock and 10:30 on Friday mornings. Those are the hours that Principal Wilson has determined should be office hours for everybody. But I teach the UU physics class and they meet on Fridays during that time. So I can't be here for office hours during those times, but I am available other times. If you have a question, well, your first line of defense should be to go to the tutors. We've got lots of tutoring hours for you. That should be your first line of defense. If the tutors are unable to answer your questions, send me an email. And if I can't respond adequately via email, I will set up a Zoom meeting where we will talk face-to-face live, even though it's not 9 o'clock on Friday morning. I will, I'll set up a meeting and we'll talk live. But you got to send me an email telling me that you need help. Don't come later and complain. Okay, let's see what else. Today, we're going to finish up chapter 14 and start into chapter 15. So it's a good time to start thinking about when our next test is going to be. My plan is that when we finish chapter 15, that's when we'll take the next test. So I'm thinking maybe a week and a half from now, approximately. We'll see how things go. So you should start planning that there's going to be a test in about a week and a half. So make sure you get in all your late homework assignments. Make sure you redo any quiz retakes. Don't have a whole lot of time left to do that. Okay, any questions about any of that before we talk about last night's homework? All right, not seeing any or hearing any. Okay, well, let's see what we have about last night's homework. Okay, so here are the answers to the ones that you haven't already looked up. So as usual, we're not going to have time to go over very many of these. So if you could only see one, what would you want that one to be? All right, I'm seeing a bunch of votes for 83 and 94. Looks like it's kind of evenly split between 83 and 94. Okay, well, let's try to do both. If we do them quickly, I think we can get both of them in. 83, I believe that was the earthquake one, right? Yep, okay. Oh, where is it? Back of the chapter there. Here we go. Okay, yeah, that's the earthquake one. Now, on that one, the physics, I would hope, is pretty straightforward. I know from past experience, what gives people trouble is just the mathematics. So this is a great exercise in mathematics. All right, let me open up a whiteboard. All right. So what's happening here is, here's the ground, and here we are standing Okay, and an earthquake happens right here. All right, now, interesting thing about earthquakes is that when they shake the ground, you get two kinds of vibrations. Some of the vibrations, so if you were to look at a piece of dirt in the ground, you would find that as a result of this earthquake, that dirt moves forward and backward, which is the same direction. So the wave of the earthquake is going to travel from there to us. So if you look at a piece of dirt on the ground, you're going to find that sometimes it's going to be vibrating in the same direction, parallel to the direction that the wave travels. And hopefully by now you guys realize that that's called a longitudinal wave. So that's like sound waves are. But with many earthquakes, maybe not all, but many of them, in addition to a longitudinal vibration, it also sets a vibration where if you were to look at the dirt, you would find that the dirt vibrates in a direction that's perpendicular to the direction that the wave is traveling. Okay, so we would call this a transverse wave. And so many times when an earthquake happens, you get both waves created from the same earthquake event. And these waves travel at different speeds. So in the problem here, they're saying that the transverse wave travels, and so I'm going to call it VT, and they're saying it travels at 8.9 kilometers per second. Now, kilometer is not a standard physics unit, but sometimes you can get away with using that. All right, now the longitudinal wave travels more slowly. So I'm going to call that VL. And so that travels at 5.1 kilometers per second. All right. All right, so they both start off at the same time because the earthquake, happens, it starts them both going. So since the transverse wave is traveling faster, clearly that's going to get to us first. So we have a sensitive seismograph that can tell the difference between a transverse and a longitudinal wave. And so what we find is that the slower wave arrives 68 seconds after the faster wave arrives. From that, we can tell how far away the wave was, how far away the earthquake was. All right, so this distance right here is what we want to calculate. All right. So not really a lot of physics in this problem. I mean, understanding what a transverse wave and a longitudinal wave is, that's physics. But I mean, the rest of it is just a math problem. And heck, even Mr. Jensen should be able to do this. And by the way, you can tell him I said that. In fact, please do tell him I said that. Okay, so how would Mr. Jensen go about doing this? Well, he's going to recognize that the waves are traveling at constant speed. So we don't need to do all those fancy Dr. Seuss equations. We can just use everybody's favorite equation, dirt. Distance equals rate times time. Okay, so the distance, let's do it for the transverse wave first. All right, so the rate of the transverse wave travels is 8.9 times t. Now, we don't know how much time it takes for the transverse wave to get there, so we have to just leave it as a t. And I'm going to put it as little t subscript big T, meaning the time of the transverse wave. All right, so we don't know d, we don't know t. Rats. Got two unknowns and only one equation. If you got two unknowns, how many equations do you need? Two. Where are we going to get the other equation from? Well, let's look at the longitudinal wave. Okay, so again, distance equals rate times time, just like before, and it's the same distance, so same d. The rate is different this time, it's only 5.1. And t, this is the longitudinal time, but we know that longitudinal time is 68 seconds more. So let's just keep life simpler here. Instead of calling it TL, let's just call it TT plus 68. So there you go. Two equations, two unknowns. No problem, right? And they're both already solved for D. So what we can do then is we can just say, well, then this must equal that. So what we can do then is let's say that this must equal 8.9 times T, and so TT. Okay, so there you are, one equation, one unknown. From this point on, we can hand it off to a ninth grader and let a ninth grader take it. So what would the ninth grader do? Well, let's see, let's clear a little space here. All right. So what would your ninth grade teacher tell you to do? Well, how about we distribute this out? So we're going to get 5.1 times, I'm just going to call it T, and we just understand that it's the transverse time. Okay, plus we have 5.1 times 68. What is that? 5.1 times 68. Okay, so I'm getting 346.8. Okay, so that is equal to 8.9 times T. So if I subtract a 5.1 T from each side, so 8.9 minus 5.1, okay, so it gives me 3.8. So 346.8 equals 3.8 T. That's a 3. It may not look like it, but that's a 3. Okay, so divide both sides by 3.8. So 346.8 divided by 3.8. And so I get 91.3. So T equals 91.3 seconds. Remember, this is the transverse wave. This is the faster wave. All right, so that's nice, but that's not what we're after. What we're after is D, but that's okay. This equation right here. Once we stick that in there, so let's just take our answer, multiply it by 8.9, and we get 812. So D equals 812. All right, now the last thing we do is we ask, are we allowed 3 sig figs? And I look here and I'm thinking, looks like our input numbers only have 2 sig figs. So we'd better round that down to 810. Okay. So that earthquake that occurred, it was 810 kilometers away, and hopefully that matches what we've got here. Yep, it does. Okay, good. All right. Any questions about that? All right. Okay, good. And so the other one was 94. And I think we have time. So let's go ahead and do it. So 94 says we got a spring with a mass. Okay, so let's open up a whiteboard. All right, so here's the ceiling. We've got a spring here. Okay. And so it's got a mass on it. And so if the mass was not there, this is where the spring would be. But because we hung the mass on there, that's going to stretch it down 9.4 centimeters. Now, a centimeter is not a standard physics unit, so we've got to be careful. You might get in trouble with that. Okay, so now this is where it sits with the weight. So this is our new equilibrium position. And so what we're going to do is we're going to pull it down even more from that. We're going to pull it down to here at another 8.0 centimeters below our new equilibrium point. And we're going to release it. So it's going to go up and down and up and down and up and down between these here. So we want to find the spring constant. Well, okay, this will give us the spring constant right there. So we know that F equals Kx. Now, sometimes we put a minus sign there and sometimes we don't, depending on whether we're talking about the force that we exert on the spring or whether the force that the spring exerts on us. But if all we care about is the absolute value of it, well, then we don't really need that minus sign there, because I just want to know the magnitude of the force. The direction, I can tell from the picture what the direction is. All right, so the magnitude of the force, well, that's just mg. And so K is what we're looking for, and X, we know what X is. And so K then is going to equal mg divided by, and I like to put a delta X in front of here, just that's how much it's stretched. Okay, so we know what M is, we know what G is, we know what delta X is, that X, no, okay. So M was, oh boy, they don't like standard physics units here, or at least they're not using. I'm going to put them in standard physics units. That's always the safest way to go. So 225 grams, that would be 0.255 kilograms times G, which is 9.8, divided by delta X, which is 9.4 centimeters, so 0.094 meters. It's always best if you work in standard physics units, okay? All right, so we got kilograms, we got 9.8 meters per second squared. All right, so when we do that, that'll tell us what K is. So 0.225 times 9.8 divided by 0.0994. All right, so that gives me a K value of 23, whatever units it is we measure spring constants in, which if we take all these units here, it's kilogram, meter. Here I got too many windows in the way here. Meter per second squared, and on the bottom we've got meters. So that cancels that. So there we go. Or we could kilogram meter per second squared. That's the same thing as a Newton. But let's not get hung up on units. The number is 23 as long as we use standard physics units. Okay, so we also want to know the maximum speed. Okay, this one is a good one. There's a couple of ways we could do this, but the easiest way is to look at energy. So if this was the equilibrium position up here and we stretch it that much, so we know that the spring potential energy is 1/2 kx squared. And we didn't know what K was before, but now we do. And this X is, this is the new stretch there. So our spring potential energy is 1/2 times K, which is 23, times X, which is 0.08. Remember, we want to use standard physics units, squared. All right. So compared to the equilibrium position, when we pulled it down an additional 8 centimeters, we gave it an energy of 1/2 times 23 times 0.08 squared. So it had a spring potential energy of 0.0736 joules. That's how much spring potential energy it has when it's down at the bottom. Okay. Now it's gonna vibrate up and down and up and down. Let me clean this out a bit. Okay. So here's our equilibrium position. So it's going to go shooting up to here, and it's going to come shooting down to here again. So when it's passing through the equilibrium position, the energy is all going to be kinetic. Because remember sigma E, so that's going to be, it's going to be the potential energy plus the kinetic energy. And if we've got gravitational potential energy, that confuses things. But if we let this be our H equals 0, you can define your origin anywhere you want. Okay, so actually, we can put. Well, I'll tell you what. Most people like to define it down to the bottom. So I won't confuse you here. Let's define it down to the bottom. Okay, so let's say that our energy is down this, whoops. Okay, so this is the bottom. This is H equals 0. All right, so let's set up our conservation of energy equation. So, sorry, it takes a while to erase here. Okay, so we're going to say the total energy at the bottom has to equal the total energy anywhere else. So I'm gonna focus my attention on this. I'm gonna call this the equilibrium position. So I'm gonna say E, so this E he means stands energy. This E stands for at the equilibrium position. So down at the bottom, okay, let's see what might we have. We might have kinetic energy. We might have we might have gravitational potential energy, and we might have spring potential energy. And these are all at the bottom. Now, notice I said might, because actually we're not going to have any kinetic energy. When we pull this down and we hold it, okay, and let go of it, it starts off with no kinetic energy. But I like to put it there just so we don't forget it. Now, up at the top, or at the midpoint here, what we have? Well, also down at the bottom, we're not going to have any gravitational potential energy either, because H equals 0. So when we're down here at the bottom, the only energy we have is spring potential energy. So when it comes up to here, well, what are the energies that it might have? So it might have kinetic energy, and in fact it will. It might have gravitational potential energy, when in fact it will. And I like to write in spring potential energy because in general it might have it. But if we are interested in this point right here, this is the point which is the equilibrium position. And so it's not going to have any spring potential energy at that point, at least not that we care about, because when we calculated how much spring potential energy it had, this position right here, that was our 0 point. That was the point we chose as our 0. Okay, so what we have there is the spring potential energy must equal kinetic energy plus potential energy. Well, we know how much spring potential energy we have. It's this. Okay, so if we bring this down here, so we have 0.0736 has to equal the kinetic energy, which is 1/2 mv squared, plus the potential energy, which is mgh. And so we know what m is, we know what g is, we know what h is. H is this height right here, which was 0.08. G is 9.8. And m, we know they tell us what m is somewhere in here. Yeah, 225 grams. Okay, so m is 0.225 kilograms. If you work in standard physics units, you'll be the safest. All right, so, and that goes in here and here as well. All right, so do we really need to keep on going? I mean, we've got it down to this point right here. All we have to do now is just solve for V. And I don't think that it's really worth the time taking to do it. I would hope that from this point on, you guys could now solve for V. We know M, we know G, we know H, we know the spring potential energy is that. So from this point on, we hand it off to a 9th grader, and they do their magic. And when they're done, hopefully, if everything goes right, the answer they get will be 0.79 meters per second. So that one was a good problem. Okay, that's one that I think even Mr. Jensen might have struggled with that one if it's been a while since he took physics, and he would have to think about, yeah, conservation of energy, spring potential energy, yeah. So he might have to rack his brain there. Okay, but if you give him a little help with the physics and let him do the math, hey, we could do this. Okay, any questions? All right. Okay, so 94 was a good problem. That one really was a challenge. 83 is mostly just a math problem. Okay, so let's talk about new stuff here. So today we are going to start into chapter 15, which is dealing exclusively with sound. Up until now, all of the waves we've talked about could have been any kind of wave. Light waves, sound waves, earthquake waves, waves on strings, wave in water. So in chapter 15, we're going to focus in on one particular type of wave. And much of what we learn in chapter 15 is going to be relevant to other waves as well. But some of it might be peculiar just to sound, because it does have a few features that are a little different than other types of waves. All right, so first off, let's make sure we understand what is a sound wave? Well, if we take a bell and we hit it with a hammer, okay, so what's going to happen is the surface of the bell, it's going to go out a little bit, and then it's going to come back a little bit, and then go out again and come back in. So the surface of the bell is going out and in and out and in. Every time it pushes out, it creates a region of high air pressure. Okay, and so these dark areas here, these are all intended to be areas of high air pressure, and these are going to be traveling outwards. And then when the bell comes back in again, well, that's going to create a region of low air pressure. Okay. So what we get are regions of high air pressure traveling outwards, followed by regions of low air pressure traveling outwards, followed by another region of high air pressure traveling outwards. Okay. And so if you were to look at any one air molecule and see what's happening to it as these successive waves travel outward, okay, when the air molecule is being pushed by this high pressure, it's going to move that way. And then after the high pressure region passes and we get a low pressure region, the air molecule is going to be that way. Okay, so the wave itself is traveling this direction. If you look at the molecules in the medium, you'll see that they're traveling parallel to the direction the wave is traveling. So hopefully you guys realize this is what we call a longitudinal wave. And so, oops, wave, not way. Okay. All right. So this is different. I mean, up until now, we've been dealing with waves on strings, and this is a different kind of a wave. So you might think that, that we're going to have to do the mathematics differently or whatnot, but in fact, the mathematics are going to be exactly the same as they were before. If we just graph the pressure as a function of distance, right? So wherever you see the slinky here is compressed together. So a slinky wave and a sound wave are the same. So wherever you've got the high pressure region, we show that like this. Where we have a low pressure region, we show it like this. Here's another high pressure region, we show it like this. And so if we just make a graph of pressure as a function of time, you can see that graph looks exactly like the string wave that we're used to dealing with before. Okay, so even though the motion of the molecules is left and right, we can graph it as being up and down if we graph it as pressure. So mathematically, there is no difference at all between a longitudinal wave and a transverse wave if we just treat it like this. So hopefully you guys agree this is pretty straightforward. So all of the mathematics we did before, we can still use it again. Okay, so now, what is it that determines the speed of a wave? We've talked about this many times. Hopefully you understand. The answer is properties of the medium. Remember last time I had that software simulator where we changed the frequency and we saw that as the wave pulses traveled down the string there, if we looked at how fast they were traveling, we could change that frequency to anything we want. It didn't affect the speed of the waves. We could change the amplitude to anything we want. Didn't affect the speed of the waves. The only thing that affects the speed of the waves is properties of the medium. So what is the medium for sound waves? Well, right now, as you guys are hearing my voice, the medium that's carrying the wave is air. So what would affect the speed of the sound wave? Well, properties of the air. Okay, so one obvious one here would be temperature, right? So cold air is going to travel, the sound in cold air is going to travel at a different speed than the sound in warm air does, right? So if you want to change the speed of sound in air, well, change the temperature. Also, another thing you could do is change the pressure. Up here in Utah, where we're at relatively high altitude, the air is a little bit thinner. So it's not surprising the speed of sound here is going to be different than it would be at sea level, even if the air was the same temperature in both places. Okay. Another thing we could do is we could change the composition of the air. So from your chemistry class, hopefully you know that the air that we breathe is a little bit more than 20% oxygen, a little bit less than 80% nitrogen, and then a few other things thrown in there. What if we were to change it instead of oxygen, nitrogen? What if we were to change it to helium? What would that do to the speed of sound? A lot. Okay. The speed of sound is very different in helium than it is in air. Okay. What if you are swimming? Let's suppose that you dive down under the water, you hold your breath, dive down under the water. Somebody up on the shoreline, they set off a firecracker. You will hear it because sound can travel through water just as well as air. And in fact, maybe even better, depending on how you define better. So depending on what kind of water it is, that's going to determine the speed of sound. In fresh water, the speed of sound is this. And seawater, you guys realize, has lots of salt in it, so it's more dense. And so not surprisingly, it has a different speed. Okay. So this table here, table 15.1, I would recommend you put a bookmark there. You're going to find yourself referring back to this table many times as you do tonight's homework, because some of the problems that you solve in tonight's homework, you're going to be dealing with sound and air. Others you're going to be dealing with sound and water. And you might even be dealing with sound in other things like metal. Sound can travel in metal. And in fact, it travels really fast in metal. So keep a bookmark here. You're going to find this will come in very handy. So like, for instance, one of the problems you might see in your homework tonight would be, let's suppose that you're standing here and you're standing next to a really big cliff and you shout, "Hey." Okay, so the sound wave travels to the cliff, bounces off the cliff, travels back, and you hear the echo. And so in your homework, they're going to say, all right, well, let's suppose that the time between when you say "hey" and when you hear the echo, let's say that time is 1.7 seconds. And so you want to know, how far is the cliff? Okay. All right. Well, is the sound accelerating? If it's accelerating, then you're going to need to get out the Dr. Seuss equations, but there's no reason why it would accelerate, because the medium is the same here as the same here as same here. Well, it's safe to assume that it's the same temperature, same everything. So it's going to travel at a constant speed. So you don't need all those equations and motions we did before. You can go back to everybody's favorite equation, dirt. D equals R times T. So if they tell you what T is, and you look and they tell you what the air temperature is, let's say it's 20 degrees C. By the way, this is Celsius. Remember this, we're using commie units here. None of this Merkin stuff. So we know what the speed of sound is. So you stick it in here and you get the answer. And so let's say we take 343 times 1.7 and we get the answer. We get 583.1 meters. And we feel really good about it. And we look in the back of the book and we find out they got a different answer in the back of the book. What did we do wrong, guys? Why is this not the right answer? Anybody want to unmute yourself and tell us? Why are they going to have a different answer in the back of the book?
Because you're hearing the echo.
And
so it goes like twice the distance.
That's it exactly. Yes, this distance here, this is the distance that the sound traveled. Okay, so the sound traveled to the wall and back. Okay, so we only want to know the distance to the wall. So we really shouldn't call both of these D. We should call this we should call this dW, and we should call this ds, where ds means the distance that the sound traveled. So the sound traveled to the wall and back. So what we need to do is we need to take this answer and we need to divide by 2. So be careful, don't go making that mistake. I mean, every year I always get students to say, Mr. Hendricks, the answer that I got is not the same as the answer in the back of the book. What went wrong? Well, this is most likely going to be what went wrong. So be careful about that. Okay. All right. New subject. When you say that one sound is louder than another, and you want to somehow put a number on how much louder it is, I'm willing to bet that most of you realize that the loudness of sound is measured using a unit that's called decibels. So it's abbreviated as dB, and that stands for decibel. Okay. And so most people, they think that decibels work kind of like other units that we're used to. So if I were to tell you that the siren on a police car is 100 decibels, and as you and I are having a casual conversation right now, if I were to get out a sound volume meter, and and it would probably tell us that the sound of my voice that you're hearing right now is going to be around 50 decibels. So if I were to ask you how much louder is a police siren compared to our conversation, you'd say, well, that's 100 decibels. This is 50 decibels, therefore is twice as loud, right? Well, that's not the way that decibels work. This equation right here, this is how you calculate decibels. And you can see that there's a logarithmic relationship. Okay, so before I go into too much more here, I should probably pause for just a second and let me ask you if you have worked with logarithms before. So I'd like you to please type into the chat box, yes, if you have worked with logarithms in your math class before, or no, if you have not. Or maybe it's say yes, but I never really understood it. That's a possible answer. And if you want to put it in as a private message so that you're not embarrassed, then that would be fine. So I see all of the answers are yes. A couple of the private answers that I'm getting are no's. So it looks like most of you have worked with logarithms before. But a few of you are saying that, yeah, it's been a while and I need a little bit of review. Okay, so since most of you said yes, I won't go into too much detail, but because a few of you said no, that's probably good. Let's do a super quick review of logarithms and how logarithms work. Okay, so logarithms can have different bases, but the common log is base 10. And that the common log is the base that's used for the decimal system. Okay, so if I want to take the log, the common log, base 10, of the number 1,000, okay, the quick and dirty simple explanation would be just how many zeros are there, okay? So the log of 1,000, it has 3 zeros, therefore the log is 3, okay? The log of the number 100, well, it has 2 zeros, so that means the log is 2, okay? And then the log of 1 million, okay, well, that has 6 decimals, so the log is 6. Now, some of you who haven't had logarithms might say, well, what if it's not a nice multiple of 10 like that? What if I want to take the log of 85 or the log of 112? Okay, well, it's going to be a little bit different. I mean, if I want to take the log of 112, okay, you can see it's going to be some number. It's going to be more than 2. It's going to be less than 3. It's going to be somewhere in between there. So I don't want to go into too much detail about it, what I'm going to do is in this class, I'm going to keep it really simple. So we're always going to take logs of either 100 or 1,000 or 1 million. We're not going to take the logs of any numbers in between. Your calculator can do it. Okay, so the way that sound volume is defined is you look at the intensity of the wave. So this, I think this is the first time that I've used the word intensity. So maybe I should define what intensity is. Intensity is a measure of how much power the wave has. So the power of the wave. So you guys know that waves can deliver power. So if I take a wave, okay, and I shake my right hand, okay, so I'm giving energy to the string transfers energy to my left hand. And so if I put a wave pulse in here, so this pulse moves over here, it hits my left hand and wants to pull my left hand up. So I can deliver energy from my right hand to my left hand through the string. And so if I measure how much power I'm delivering, then that is the intensity. And so let me just go with the letter I here. So I is the power delivered by the wave. And hopefully you guys know the power. Remember power, the definition of power? It's how much energy per second. All right. So a sound wave can deliver power. If you stand too close to a jet engine, that sound wave is delivering energy to your ear, and it can deliver so much energy to your ear, it can cause physical damage to your ear. All right, so what we're going to do is we're going to pick some reference level. And so over here on the left side of the graph here, this is going to be what we're going to call 0 decibels. And so that is the lowest sound that, so when you get down to 0 decibels, you can't hear it anymore. The human ear can't. Now, if you have a really super sensitive equipment, the equipment might be able to hear it, but this is the point where the average person would say, I can no longer hear it. And so if we go up to 10 decibels, okay, so that would mean that the power that's delivered by the wave there is given by this formula. So at 10 decibels, the power that's delivered by the wave would be 10 times more than this wave, which a super sensitive instrument would be able to pick up, but the human ear would not. So think of it this way. Let's suppose we have 2 sound waves, and one sound wave has an intensity that is 100 times the intensity of another sound wave. So let's say this is wave 2 and this is wave 1. So if I have 2 sound waves and one of them is the power that's delivered by the wave is 100 times greater than the other. Okay, so what I can do then is I can take the ratio of I2 divided by I1, and that's going to be 100 times I1 divided by I1. Notice the I1s cancel out. So this term right here, if I'm just talking about these 2 waves, okay, so I have 100 divided by 1. So the number that goes in here is 100. So what is the log of 100? Well, the log of 100 is 2. Okay, so that's 2. So then I'm going to take 10 and I'm going to multiply that by 2. So that means 20 decibels. So if I have 2 sound waves and one of them is 100 times greater than the other one, then I would say that this sound here is 20 decibels greater than this sound. Okay, does that make sense? All right, so here's a good way to think of it. Okay, let's suppose that I've got all these different sounds that range from 0 decibels up to 140 decibels. So in your homework tonight, what they're going to do is they're going to ask you a question. Like they're going to say, let's suppose that I have a sound that is 80 decibels, and I've got some other sound that is 40 decibels. And I want to know how much greater is the intensity of the 80 decibel sound compared to the 40 decibel sound. So I want to know how many times greater. Now, somebody who doesn't understand physics, they would say, well, 80 decibels, if I divide that by 40 decibels, I get 2. So most people would say that an 80 decibel sound would be 2 times as loud, 2 times the intensity of a 40 decibel sound, but that's not the way it works because it's got this logarithmic thing here. So here is the trick. So everybody get out your notebooks and write down what I'm about to do. When we're talking about the relative intensity, the rule is that every time you go up by a factor of 10 in decibels, that is a 10x increase. So if I go from here to here, that's a 10x increase. From here to here, that's another 10x. From here to here is yet another 10x. And then finally from here to here is another 10x. So does that mean that the total is 40 times greater? No, because it's not 10 plus 10 plus 10 plus 10. It's 10 times 10 times 10 times 10. So 10 times 10 is 100, times another 10 is 1,000, times another 10 is 10,000. So if I go directly from here to here, that would be an increase of 10,000 times. So this 80 decibel sound wave is 10,000 times the intensity of a 40 decibel wave. Okay, that makes sense? So this equation right here, I am not going to require you to use that equation because I recognize that some of you are not really familiar with logarithms. So I'm just going to expect you to memorize the rule. So the rule says every time you go up a factor of, up by 10 decibels, the intensity goes up by 10. So if I go from 100 decibels up to 130 decibels, and I want to know how much more is intense is the 130 decibel sound than this one is. So we got 10 there, plus another 10 there gives me 100, plus another 10 there gives me 1,000. So that means if I go from here to here, it's 1,000 times as intense. Pretty straightforward. Any questions about that? Okay, not hearing any questions. Okay, now, having said that, I am now going to confuse things a little bit, not because I want to, but just because you need to know. There are lots of different ways of talking about the volume of sound. Up until now, we've been talking about the intensity of the sound, where we've been talking about the power that is delivered by this sound. But a lot of people don't really care about the power that's delivered by the sound. They just care about how much does the human ear perceive it to be. And the human ear does not perceive power the same way that an electronic instrument would. With a human ear, the rule is that if you go from 40 decibels to 50 decibels, most people, not everybody, but most people will perceive that as being approximately a 2x increase. So if I say hey, and I do it at 40 decibels, and then I come back again later and I say hey, and that time it's at 50 decibels, okay? Most people will perceive that as being a 2x increase. So we've got a couple different ways of measuring measuring it. And so so write this in your notes here. So if we are talking about perceived loudness, we're not talking about the actual power that delivered. We're just talking about how much difference most people will register in their brains. Every time you go up 10 decibels, that's a perceived increase of about 2. Okay, so in your homework tonight, if they were to ask you, what is the perceived difference in loudness between a 40 decibel sound and a 70 decibel sound? Well, you say to yourselves, okay, from 40 to 50, that's 2. 50 to 60, that's another 2. So that gives me 4 now. 60 to 70, that's another 2. So that gives me an 8. So if we're talking about perceived loudness, a 70 decibel sound will be perceived by most people as being 8 times as loud as a 40 decibel sound was. So if we're talking about perceived loudness, that's the way that it goes. But in your homework, they might not ask about perceived loudness. They might ask about intensity. And they might not call it intensity. They might call it power. Okay, so if we're talking about power, from here to here, that's 10. And here to here is another 10, and here to here is another 10. So if I go directly from there to there, if I go directly from here to here, and if what I'm interested in is the intensity, then 10 times 10 times 10, that would be 1,000. Okay, so the answer might be 8 times or it might be 1,000 times, depending on whether they're asking about perceived loudness or whether they're asking about the difference in the power that's delivered. Okay. All right, so I see a question in the chat box saying, does it always go up by 10 for any number? And if I'm understanding your question correctly, the answer is yes. So it doesn't matter if I'm going from 80 to 90, that would be a 10x. Well, let's see. Let me do, yeah. So if I'm going, so red ink corresponds to intensity. So if I'm going from 80 to 90, that would be a 10x increase. If I'm going from 110 to 120, that would also be a 10x increase. If we're talking about power. Now let me switch to black ink, because in black ink, we're talking about perceived loudness. So if we're talking about perceived loudness, then it would be a 2x increase. And it doesn't matter whether we're going from 80 to 90 or 110 to 120. Anytime that would go up by 1 step size, where the step size is 10 decibels, that would be 2x. If it's perceived in 10x, or yeah, 2x if it's perceived loudness, 10x if it's actual intensity. Okay. Now, let me apologize, but there is a third way that they might ask you in the book. Okay, they might ask about perceived loudness, they might ask about intensity, but they might also ask about amplitude. So let me get a different color here. Let's go with blue. Okay, they might ask about the amplitude of the wave. Okay, so if I've got a wave that looks like this, okay, so the amplitude is this much. You need to know, now I don't want to go into too much detail here. A lot of people think that if you double the amplitude of a wave, that would double the power that that wave is delivering. But it turns out that's not the case. It turns out that if you doubled the amplitude, then the power goes up by a factor of 4. So the intensity is proportional to the amplitude squared. So if you double the amplitude, the intensity goes up by a factor of 4. If you triple the amplitude, the intensity goes up by a factor of 9. So that changes things a little bit. So if I am talking about the amplitude of a wave, it's going to be the square root of the intensity. So if I go from 40 decibels to 50 decibels, that is not going to be a 10x increase. That's going to be an increase of the square root of 10. And, you know, I apologize that there are so many different ways of doing it, but hey, I didn't write the book. And that's just the way it works. Okay, so let's suppose in your homework tonight, they ask you how much more is the amplitude of a 70 decibel wave compared to a 40 decibel wave. All right, so the answer is just go in steps. So here's the square root of 10, and then here's another square root of 10, and then here's another square root of 10. All right, so that means that a 70 decibel wave is going to be the square root of 10 times the square root of 10 times the square root of 10. So in other words, it's 10 to the 3/2 power. So just put that in your calculator and see what you get. Or if they're nice to you, what they'll do is they'll say instead of comparing 70 and 40, what they might do is they say, well, let's compare 80 and 40. And the reason I say that's nicer is because then that way you don't need a calculator. So if they ask you how much more is the amplitude of an 80 decibel wave than a 40, so we got the square root of 10 times the square root of 10 times the square root of 10 times another square root of 10. Okay, so square root of 10 times square root of 10 is 10. And then this square root of 10 times this square root of 10 is 10. And 10 times 10 is 100. So that means if we're talking about amplitude, an 80 decibel wave is going to be 100 times the amplitude of a 40 decibel wave. Okay, so I realize that this is new for a lot of people and potentially confusing to a lot of people. So remember that what we're doing here is being recorded. And so later this afternoon, I'm going to put this recording on Canvas. So if you had a little trouble following what I just did, come back later this evening, watch this video a second time, pause it as many times as you need, write it down. And so after you've done a couple of the homework problems, hopefully it'll settle in. We good? All right, not hearing any questions. Okay, now there is one other thing that you're going to need for tonight's homework. And this one is one that's a little bit more fun. I think you'll enjoy this. The best way to introduce this is, let me open up my Canvas page. And I'm going to go into this page right here, which I just added late last night. So many of you haven't seen it before. Doppler effect videos. You guys know what the Doppler effect is? Well, let's find out. Okay, so let's click on that. And it's going to take us to a page where I've posted a couple of YouTube videos that I encourage you to go back and watch these videos as many times as you think you need to. My Canvas is being a little slow today here. Come on. Boy, it's really super slow right now. This is not good. Okay, here we go. All right. So what I'm going to do is I'm going to play this video for you. This is a car that is driving down the road. And so it's going to honk its horn. So listen to the sound as this car passes us while it honks its horn. You hear that? So you've all heard that before, right? Let's do it one more time just for grins, because I think this is okay. So what you just heard there, that's the Doppler effect, right? Oh, Sam is worried I've just destroyed your ears. Yeah, sorry, I should have warned you to turn down your volume first. Okay. Now, the person driving the car, the sound doesn't change for them. Okay. They hear the same sound as they're approaching the pedestrian, and even after they pass the pedestrian. The person in the car, they hear the same pitch. But the pedestrian who's standing by the side of the road, When the car is coming towards them, they hear a higher pitch, a higher frequency. And then when the car passes them, then all of a sudden it switches to a lower frequency. That's called the Doppler effect. All right. And you need to understand the Doppler effect, and you also need to be able to do some math involving it. But first off, let's do this little video here. And this explains why the Doppler effect occurs. And I think it's a really well done video. So let me play it, and then also let me make it be full screen here.
The Doppler effect. In Sheldon's words,
it's the apparent change.
Okay, it looks like I've got some delay here. My internet is being super slow here. Okay, I'm sorry that it's taking a while to buffer here. This is not good.
Change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, so hopefully that helps you understand the Doppler effect. Now in your homework tonight, you're going to have to do some problems where they tell you something like, they say that a police car has a siren, and the frequency that's emitted by the police car, the original frequency is some number, let's say 570 or whatever, okay? But the police car is driving towards you. So you're not going to hear 570, you're going to hear a higher frequency. Or if the police car is moving away from you, you're not going to hear 570, you're going to hear a lower frequency. But it gets more interesting because you might also be moving. And so the frequency that you hear is not only a function of how fast is the police car moving, but also how fast you are moving. Now, I'm going to do something that I consider to be a sin, but you guys know where I'm going with this. I think that we must derive every equation that we use in this class. It's just physicists, you should never use an equation unless you know where it comes from. Now, unfortunately, we don't have enough time to derive this equation. So what I've done here is on this same page where these other videos are, if you go down to the bottom, here is a video that derives the Doppler effect equation. All right, so if you watch this video, then you will see where the equation comes from. All right, so assuming that we watch the video, then we can then use this equation with confidence. So this is the Doppler equation, but you got to be very, very careful about your pluses and minuses when you use this equation, and you need to make sure that you understand what is what. Okay, so in this equation, Fs, that is the frequency that the source is emitting. Okay, so if you were the cop in the police car, that's the frequency that you would hear. That's the original source frequency. Fd, that's the frequency that a person would hear if they are if they're standing by this side of the road or if they're in some other car. Okay, so let's draw a picture here. So here's the police car. Okay, so it is emitting sound, and the sound travels out in all directions, not just forward, but also backward. Okay, so the detector might be in front of the car, or the detector might be behind the car. So let's say that here's the detector. So you are the person standing here. So the frequency that you hear, that will be FD. And now hopefully you guys understand why the frequency you hear is going to be different than the frequency that the cop is going to hear as she sits in her car. Okay, so V without a subscript, that is the speed of sound. Now, some people say, well, shouldn't you call it Vs then? Because then that would be the speed of sound? Well, the answer to that is no, because Vs is the velocity of the source. And I should use the word velocity and not speed, because direction is important. The plus and the minus sign, that is very, very important. So let me change the word speed to velocity. Okay, so when you see Vs in this equation, that does not mean the velocity of the sound. That means the velocity of the source. V without any subscripts, that is the velocity of sound, right? Now, where are you going to get that number from? Well, this table right here, okay? So if the air temperature, whoops, I gotta turn annotation back on again. So if the air temperature is 20 degrees, which by the way, this is room temperature. 20, and this is centigrade, not Fahrenheit. Okay, so room temperature, the speed of sound at sea level is 343 meters per second. Now up here in Utah, the air's a little thinner, so it's actually slightly different. But let's just go with sea level. Now, if it's a cold day, like for instance today, the air temperature would be a little bit slower. So in the problems that they give you, they'll just let you assume that it's room temperature. So 343 is the number that you're going to be using most of the time. But be careful, make sure you read the problem carefully, because sometimes you might need this other temperature over here. Okay, so let's go back. Let's go back up to here. Okay, so you're going to look on that table to figure out what the speed of sound is. VD, that's the velocity of the detector. Okay, so VD equals velocity of the detector. Okay, now listen very carefully to what I'm about to say because this is super important. This equation only works if we define the plus direction the same way that the author did when they derived this equation. If you talk to people who use a different physics book, they're probably going to have a slightly different equation because their author may have defined the plus direction differently. So the way that our author defined the plus direction is, oops, sorry, let me, okay, so come down to the bottom here. Our author defined the plus direction so that if you start where the source is and you draw an arrow showing the direction that the sound is traveling to get to you, that is always the plus direction. That is how our author defined the plus direction. Okay, so now let's put some numbers in here. Let's suppose that you are running toward the police car and you are running at a speed. Now notice I said speed, not velocity. So your speed is 3 meters per second and you are running toward the police car. Let's assume that the police car is moving at 19 meters per second and the police car just happens to be moving in the direction towards you. So when you go putting in your numbers here, what is it going to be? So VD now, notice that your direction is opposite the direction that the sound travels. So the number you put in for VD has to be a -3, not a +3. What about VS? Okay. Well, the car is traveling the same direction that the sound is traveling. So VS is going to be a +19. What about V? Remember, V is the velocity of sound. Well, by definition, the velocity of sound is always going to be positive because that is how we chose our plus direction. The direction that the sound travels to get from the source to you, that's how we chose our plus direction. So the velocity will always, always, always be positive. And if the air temperature is room temperature, then when we look on the table, we'll find that it's 343. Okay, so then if they tell us that the source frequency is some number, let's say 570, so we plug that number into there, plug this number in here and also in here, plus this number in there, plug this number in there, and whatever pops out, that's our answer. Okay. Now, do we have enough time to do one more really quick one? Yeah, we don't really have enough time to do another one. So just be really, really careful. Make sure that before you put any numbers in the equation, draw a picture, draw an arrow that goes from the source to the detector. And remember, maybe the detector is behind the source. Maybe it's in front of the source. Always draw an arrow going from the source to the detector, and that is the plus direction. And then based on that, that'll tell you whether VD is positive or negative and whether VS is positive or negative. But remember that V without a subscript is always, always, always positive. So every year, the thing that gives students the most trouble on this is the pluses and the minuses. They aren't careful enough with their pluses and minuses. As long as you're careful, you should have no trouble with the homework tonight. Okay, speaking of homework, you probably are wondering what the homework is. Now, you of course know that you can always look on Canvas and you'll find it there on Canvas. Oops, that's not the one I wanted to share. Sorry, wrong one there. This is the one that I wanted to share, this one right here. Okay, so there it is. I want you to make sure you, oops, 10. Why the heck did I say 10 there? That's chapter 15 is one you should be reading, not chapter 10. Okay, so make sure that you read the first part of chapter 15, problems 1 through 10, and then also I want you to do problem number 14. Okay, so the bell should be ringing right now. You can type bye in the chat box and head out. If you have a question you want to discuss, I'm willing to do that. Here, I'll turn off the recording so we can do it in private.